All right, this is our third video. In it, we're going to go ahead and do a quick review again, and then we'll finish talking about how we finish the breakdown of carbohydrate to get all the energy out of it that we can get, and then we'll look a little bit at how we harvest energy from lipids or fat. And so you look over here to the right, and what you see, of course, is glycolysis. Again, here is the glucose molecule. It enters the cell, and it's immediately phosphorylated. It becomes glucose 6-phosphate. Again, you know that's chemical work, and it requires the input of energy, so we've used an ATP. We change it to fructose 6-phosphate, and then we go ahead and we phosphorylate it again. We make it into fructose 1,6-bisphosphate. Well, again, we have to hydrolyze ATP in order to make that happen because it's chemical energy. But what we end up with is we end up with a molecule which now has more energy in it than the glucose did when it first entered the cell. Over here you can see the glucose coming in. Don't forget, it gets into the cell via facilitated diffusion. Well, then the next thing that we do here is we chop the fructose 1,6-bisphosphate in half, and we have a 3-carbon piece that's phosphorylated and a second 3-carbon piece that's phosphorylated. You know that we refer to that as cleavage, chop it in half. Well, then everything that happens here will happen twice. Once for this piece, once for this piece. And we quickly go through a redox reaction. We get some NADH. As you know, those are going to be sent off to electron transport to get even more energy from them. Well, now we finally start to harvest some energy. And so we have a compound here that has a high energy bond, and we're going to hydrolyze it in order to take phosphate and stick it onto ADP to finally get some ATP out. Well, we go through a few more reactions, and finally we get down to the very last one. And again, we have a compound right here with a high energy bond. We hydrolyze it, and we use that energy to do the chemical work of adding a phosphate to ADP to get ATP again. And so we end up with pyruvate. You know that this is slow glycolysis, and this very last piece that we've looked at is what's known as the common pathway. The common pathway is where we finally start to harvest the energy that is in the fructose 1,6-bisphosphate. And we also looked at this, and so we just went through glycolysis. And in particular, we went through slow glycolysis. We did get some NADHs, which go down to electron transport. Don't forget, that's occurring in the cytoplasm. The NADHs need to be moved into the mitochondrial matrix to participate in electron transport. And all the rest of it, stage 2 and stage 3 and stage 4, all are occurring in the matrix of the mitochondria. Stage 2 is pyruvate oxidation. We go through a redox reaction. We get NADHs, and we also create acetyl coenzyme A, which is the very, very first substrate for the Krebs cycle. And then there we go through the Krebs cycle. We get even more reduced compounds to send to electron transport, so we've got lots of electrons to send down through there. And so stage 2, then stage 3, and then we finish up with stage 4, which is electron transport and oxidative phosphorylation together. Separate processes, different jobs, but they're almost always linked. And so that's why we list them together as stage 4, and we don't break them up. All right, just quick review of the mitochondria. And here, mitochondria is the powerhouse of the cell. It's the organelle where the majority of ATP is resynthesized. And it's important that you understand that the pieces of the mitochondria that play a role here. And so here we have that outer membrane, phospholipid bilayer, even though they're not showing it to you. And so it's that cut piece right there. Well, then we also have an inner membrane. It's a little bit of a unique organelle because there's an inner membrane that is here, which is inside the organelle itself. In between the outer membrane and the inner membrane, we have this intermembrane space. Maybe I should have picked a different color, huh? And then lastly, what we have is the mitochondrial matrix. Here it is, deep inside that inner membrane. This is a watery solution, which is where much of the chemical reaction would occur that results in the creation of energy for ATP. Here's a slightly different depiction. You can clearly distinguish between the outer membrane, the darker brown, and the inner membrane, the kind of the beige or tan colored piece. Don't forget, membrane. So both of those are phospholipid bilayers. whoops, I'm sorry. The intermembrane space is right in here. It's between. Inter means between. It's between the outer membrane and the inner membrane, and it even includes these areas where the inner membrane is folding back to increase surface area. And then lastly, sorry, I'm getting ahead of myself. Lastly, we have the mitochondrial matrix, which in this depiction they're showing in blue because it is mostly water. But again, lots and lots and lots of stuff going on in there. I really don't care whether you know what the cristae are or not. That's not important. Not important. And then here's just another depiction that you can look at. Now, almost always, we show the mitochondria as this bean-shaped organelle, and probably that's not accurate. It's probably more of a reticulum or a network. And so maybe we'll see that at some point in physiology books that come out. Again, after we go through glycolysis, then we go through pyruvate oxidation. This is stage 2. And we're going to take the pyruvate. Don't forget, when we break down a glucose molecule, we'll have 2 of them. And so here is the pyruvate, 3 carbons, and we do a redox reaction. We give NAD some electrons. We reduce it to NADH. Again, goes off to electron transport. We bring in coenzyme A, and what we're going to do is we're going to go ahead and we're going to actually get rid of one of these carbons. And we get rid of it in the form of CO2. You know that's going to move into the blood. Most of it will be carried by the bicarbonate ion and taken back to your lungs so you can breathe it out. And again, we end up with, our acetyl-CoA. And you know that acetyl-CoA, at least I hope you know, the acetyl-CoA is really the first substrate for the Krebs cycle, which we'll look at in a bit. But here you can see just a different depiction of what I just showed you. So here to the left is the pyruvate, and then we go through the redox reaction. We get NADH. We also take off one of the carbons as CO2. And here what we have is the acetyl-CoA that's going to kick off the Krebs cycle for us. And so now we've actually seen stage 1 and stage 2 of the complete breakdown of glucose. Summary of this: it occurs in the mitochondrial matrix, doesn't require oxygen, doesn't need it. Byproducts are NADH and CO2. And again, here you can see we're looking again at pyruvate oxidation. There it is. And so we see what we just talked about. These 3 things represent the carbons. We chop off 1 carbon, release it as CO2. We reduce NAD to NADH. We end up with acetyl-CoA. And now we start the Krebs cycle. And so the initial substrates are oxaloacetate, OAA, plus acetyl-CoA, and they will combine to yield citrate. All right, and then we go through a whole bunch of reactions. We get way over here to the end, and malate is going to be converted to OAA again. And so you can see that OAA is both one of the beginning substrates, but it's also the final product. And that's why we call this thing a cycle, and that's why 99% of the time it's drawn in this circular fashion. We could draw it in a straight line. It wouldn't matter. And then you've also noticed that we've got a bunch of redox reactions. And so 3 different times we reduce NAD to NADH, and once we reduce FAD to FADH2. Lots of electrons to send to electron transport chain. Don't forget that this is happening in that mitochondrial matrix, and so we're nice and close to electron transport. And then lastly, we're going to produce an ATP, and we're still breaking down the molecule. So we take carbon number 2 and convert it to CO2, carbon number 3, convert it to CO2. Now, if we go through 2 turns of the Krebs cycle, we've gotten rid of all the carbons that was in that initial glucose. C6, H12O6, well, 3 CO2s here, 3 CO2s from the second pyruvate. It's all gone. It's all gone. Okay, and so again, the Krebs cycle is happening in the mitochondrial matrix. It does require O2 for it to continue. Otherwise, we can't continue to reduce the NAD and the FAD. We get 1 acetyl-CoA resulting in 3 NADHs, 2 CO2, 1 FADH2, and 1 ATP. So just remember, 3211. 3211, it's kind of like a phone number. You just have to remember what goes with the 3, the 2, and the 11. So there you go. And here's, we move on to electron transport. Again, the Krebs cycle was happening here in the matrix. That's where we are. Here's the intermembrane space. Here's the matrix. And so the NADHs and the FADH2, they just move up here to the inner membrane and dump off their electrons to the electron transport chain. And so we oxidize NADH to NAD. So this is a redox reaction. The electrons go from here to here, that's a redox reaction. They go from here to here, that's a redox reaction, and so on and so forth. Now don't forget that in redox reactions, not only do we have transfer of electrons, as they're showing you here, but we also have a transfer of energy. The energy of these redox reactions is what is used to power the pumping of these protons from the mitochondrial matrix into the intermembrane space, where we have a very, very high concentration of protons. All of these positive signs that you see up here are supposed to represent protons. And so that is the one and only job of the electron transport chain. Here you can see the final electron acceptor. These electrons can't just float off into the mitochondrial matrix. We have to have some substance pick them up. And so we take molecular oxygen, we chop it in half, it picks up electrons being carried by the hydrogens, and you know oxygen and two hydrogens become water. And so there you go. And so this is the one and only job of electron transport, create the proton gradient, which then gets used by oxidative phosphorylation. And so here you see these protons, they want to move back across the inner membrane into the matrix and try to reestablish equilibrium. We're not going to let that happen. But that's where we get the energy to drive the chemical work of phosphorylating ADP to ATP. Oh, look, here's an example of an exception, biological work being done, which is not powered by the hydrolysis of ATP. So there's an example of that. And so this is the oxidative phosphorylation piece of it over here. So there you go. All right. This, by the way, is another example of biological work being done that isn't powered by hydrolysis of ATP. We're pumping protons against their concentration gradient, and we're making that happen using energy from redox reactions. So good stuff. And then here's just another depiction of electron transport. There's our final electron acceptor. There are the protons getting pumped across. And then finally, oxidative phosphorylation. You can look that over on your own. We don't need to rehash that. Outer membrane, intermembrane space, inner membrane, and matrix. Okay. All right. And so again, redox reactions provide the energy to pump the protons across. And so here you can kind of see a summary of what we just looked at. And so we did glycolysis in the earlier slide, and then we did pyruvate oxidation, Krebs cycle, electron transport, and oxidative phosphorylation. Okay, and this too is kind of a summary of that. And so this paler blue represents the cytoplasm of the cell. Here's the glucose, and we go through all of the different parts of glycolysis. Don't forget activation, cleavage, common pathway. And then occasionally we'll go from slow to fast glycolysis where we produce the lactate. And then again here you can see pyruvate moves into the matrix. We go through pyruvate oxidation, we go through Krebs cycle, then we go through electron transport and oxidative phosphorylation. Okay, and so here are our byproducts. This is also kind of an overview of everything. And here's the glucose coming in via facilitated diffusion, phosphorylate it right away. And again, I'm going to let you work through this and find out what's going on down here. Don't forget you need to be able to add some detail to some of the things that you see here. It's important you look it over. If you have questions, you need to bring them up. You can either meet with me individually or you can ask in class. Okay, and so now we're going to move on and we're going to look at how we get energy from a fatty acid. All right, and so we'll review that real quickly. And so the first part of this is what we call beta oxidation. We take the fatty acid and we go through beta oxidation. We're going to get acetyl-CoA, which will feed into the Krebs cycle, and then we'll go electron transport and oxidative phosphorylation. So now notice, no glycolysis. Glycolysis is only for the breakdown of glucose or a carbohydrate. So beta oxidation is the analogous step for breaking down a fatty acid, but then Krebs cycle and electron transport and oxidative phosphorylation are common to the breakdown of carbohydrate and fat, and by the way, also protein if we looked at it. So there you go. Now we're going to look at the oxidation of fatty acids. You don't need to memorize most of this stuff, but I want you to look carefully. And so over here on the substrate side, you can see, oh, we've got O2. And we also have this complex biomolecule. Over here on the product side, oh, look, we get CO2 and water, and we get ATP. And so you should look at this and you should say, well, maybe I don't know what palmitic acid is, but I know this is cellular respiration. Well, palmitic acid, as you can guess, is one example of a fatty acid. Linoleic acid is a fatty acid, and arachidonic acid is a fatty acid. Now look carefully at the fatty acid and the CO2. And what do you notice? And I hope that what you've noticed is that every single carbon in the fatty acid is converted to CO2 in the Krebs cycle. Every carbon in the fatty acid is converted to CO2 in the Krebs cycle. And I'll say it again, every carbon in the fatty acid is converted to CO2. You know that I think repetition is good for learning stuff. So repetition, repetition, repetition. All right, just a quick review. Most energy from oxidation of carbohydrates and lipids, that's where we get the majority of our energy for resynthesis of ATP. About 95% of the lipid in your body is in the form of triglycerides. Now, you know you have cholesterol, you have phospholipids, but you have far more triglycerides, which you can see down here. There's a triglyceride. Okay? Before being oxidized, the fatty acids, oh, they have to be broken off. And we do that using lipolysis. This is just like the digestion of a fat in the GI tract. We're going to use a lipase and we're going to break the fatty acids off of this thing so that we can use them. The fatty acids are going to move into the mitochondrial matrix, and that's where they will go through beta oxidation. So again, you see the mitochondrial matrix, very, very important for reactions of energy metabolism. Well, what's happening in beta oxidation? I keep pushing the wrong button. We start with lipolysis, take the triglyceride and cut off the fatty acids, and we have the glycerol. We could actually take that thing and we could build it into, this doesn't happen very easily. It's more likely that we'll send it to the liver and it will be used in gluconeogenesis. Gluconeogenesis, okay? Well, look what happens right over here. Oh, we're using ATP. What we're going to do is we're going to activate the fatty acid, just like we did the glucose. Remember, we went from glucose to glucose 6-phosphate. We activated it. We're doing the same thing here. And so that's what's going to happen here. Then we're going to take that fatty acid and we're going to break it down by cutting off 2 carbons at a time, forming what? Well, look right there. We're going to form acetyl-CoA, all right? The other thing that you'll notice is that as we go through the reactions, they actually have them backwards here. The first redox reaction will reduce FAD to FADH2, and then the next will reduce NAD to NADH, okay? But at any rate, that's what we're doing. We're going to reduce NAD and FAD. More electrons to go to electron transport. Acetyl-CoA, as you can see, it's going to go to the Krebs cycle. What happens to the acetyl-CoA? Goes to the Krebs cycle. What happens to NADH and FADH2? Goes to electron transport. All right, so there you go. Here you can see a little bit more information. And so again, what is happening here is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbon fatty acid. A little bit on the short side, but not too crazy. And so after we go through the first cycle, we're down to a 14 carbon fatty acid. It's still activated, so we'll do it again. And then we're down to a 12 carbon fatty acid. We'll do it again. We're down to a 10 carbon fatty acid. So you can see that the fatty acid is getting shorter and shorter each time. And that means we're going to cut off carbons 2 at a time. At 16 to start with, we can get 8 acetyl-CoA out of this thing. 8 acetyl-CoA. That means 8 turns of the Krebs cycle. This is great, and so that's super. That also means, oh, a total of 16 CO2. Well, that's how many carbons we had to begin with. Now, you've got to understand the interesting thing here is we don't get 8 redox reactions to reduce NAD to NADH. We don't get 8 redox reactions to reduce FAD to FADH2. We get one less, so we only get 7 of those. And the reason is that when we get down here and we've got 4 carbons, we cleave it. We actually get 2 acetyl-CoA here, not just one. Not just one. So we didn't go through 8 cycles. We only went through 7. But because we get 2 acetyl-CoA here, that's why we get 8 of these, but only 7 of these. Only 7. Okay? And again, they're going to go to electron transport, pump more protons into the intramembrane space. So there you go. So this is easy. The number of acetyl-CoA formed, take the number of carbons in the fatty acid and just divide it by 2. 20 carbon fatty acid, 10 acetyl-CoA. The number of NADH and FADH, well, do the same thing, but then subtract 1. 20 carbons in the fatty acid, 10 acetyl-CoA, but only 9 NADH and FADH2. All right, so it's not quite as hard as you might think. Here's a different one. I like this because, oh, look, we can see all the carbons. Count them. You'll count 18. And then on top of that, they've highlighted the first 2 that are going to be chopped off to become acetyl-CoA. Here's the activation. All right, and then we're going to go ahead and we're going to start through. The activation goes from ATP to AMP. That's just like using 2 ATP. So, all right, here we go. We'll go through redox reactions. Again, the truth is that we first reduce FAD to FADH2, and then we reduce NAD to NADH. Now, when we send NADH down through electron transport, we're going to pump enough protons into the intermembrane space to power resynthesis of 2.5 ATP. Makes no sense, does it? It just simply means that in order to get 5 ATP, we have to oxidize 2 NADHs. Okay, when we start with FADH, we don't pump as many protons. We only pump across enough protons to power resynthesis of 1.5 ATP. So if we oxidized an NADH and an FADH, well, look, that would be enough protons for 4 ATP. There you go. And then again, this gets cleaved and it becomes acetyl-CoA, and it goes to the Krebs cycle. Now, when we look at everything, all the NADHs, the FADH2, the ATP that we get directly, 1 turn of the Krebs cycle is going to give us 10 ATP. All right? But we're going to keep going here. And so we're going to chop this one off. Look, it's still activated, so it comes up and goes around again. And we chop it again and again and again. It's 18 carbons. What's our rule? 18 divided by 2, 9 acetyl-CoA. 18 divided by 2 minus 1, 8 NADH and 8 FADH2. So there's a rule. Okay? And that brings us to the end of energy metabolism.